Hi, we're here to present you exploring ScyllaDB's DynamoDB-compatible API. Nadav and I will make a deep dive into Alternator, which is a DynamoDB-compatible API, and get you details on how to migrate out of Dynamo into that technology. So I'm Guilherme Nogueira. I'm a technical director at Scylla. I'm always assisting users in their journey to see the ScyllaDB true potential. And I'm a geek passionate about Linux and open source software in general and help my colleagues, family to adopt open source software. Nadav?
Hi, I'm Nadav Har'El. I'm a distinguished engineer at ScyllaDB and have been working on various things in Scylla, but also on Alternator, the DynamoDB API implementation.
Thank you, Nadav. So going over the presentation agenda for today, first we're going to discuss why to move out of Dynamo. Why do customers look into reasons? What are the reasons they look towards migrating out of Dynamo? Then we'll analyze the use case, actual metrics, deployment, and costs associated with it. And Nadav will then do an Alternator deep dive, going deeper into the technology, the reasons behind each implementation detail. And then we'll also discuss how to migrate out of Dynamo, what kind of technologies to leverage, what kind of process to follow when you're migrating out of Dynamo. And last but not least, we also touch about ScyllaDB costs related to the use case that we're going to analyze. So stick with us. So as I said, why do customers move out of Dynamo? What are the reasons behind it? And as a customer, when they interact with us, they usually bring the reasons that they're looking towards a different technology to move out of Dynamo. And these are the reasons that we most hear from them. Mainly cost. So cost associated with Dynamo deployment is usually huge, it's unpredictable, and it's usually something that we hear that is easy to get started with, but does increase a lot of cost and complexity as use case scale. And that's usually what happens with use case. So you start really small, you bring in different tenants, different customers, your company grows, your use case grows, and then out of sudden you're spending millions a month in DynamoDB. And also latency and performance in general. So all the limitations that Dynamo imposes on customers, on their users, latency can be unpredictable, especially in corner cases. And technologies such as Scylla help customers mitigate that latency issues by bringing them very stable, low tail latency. And last but not least, flexibility. So users that are not necessarily running on AWS, but still want to keep running DynamoDB compatible APIs without changing them. You are able to move out of AWS ecosystem, but still you're locked into high fees as you communicate over public networks and whatnot. So going over a little spoiler, ScyllaDB can do 50% of cost of DynamoDB use cases, and that's a guarantee. So I'll touch more on the subject later, and there's a link as well if you want to get in touch with our specialists to discuss your specific use case. But in general, we are able to offer much lower cost for the same use case with increased throughput, reduced latencies, and much better performance because Scylla is designed to be much more efficient on the hardware that it's running on. So Scylla is able to reduce a lot of that cost and you get all that goodies back in terms of a reduction of your bill, your cloud spends, or even moving to on-prem and running very efficiently. So going back to the pains that cause change or customers looking to changing their database, as I mentioned, latency is a very large reason that the customer is looking to alternatives, especially when their use case is not necessarily very well distributed. In this case, we have a Zipfium distribution benchmark that we ran where the red line accounts for operations including failure, so retries until a operation succeeds. And we see that on a use case that is high write oriented and you have a lot of contention of writes, that in queuing and retrying can lead to a very large tail latency increase, especially for those use cases. If we account for the success only operations, we see that latency drops significantly, but still you're dropping a request from your end user. So in here, we see that on a 90% write use case, latency is still in the 400 millisecond range, while the Scylla line, the blue line at the very bottom, is very stable at single digit millisecond, 10 millisecond most. So this might not be the best task to put DynamoDB under. So we also ran a uniform distribution test where we compared exactly how Scylla and Dynamo operate under those circumstances. And at the bottom, we have each test that we ran, from full write test, 0% read, to all the way opposite, 100% read, 0% write. And we see that ScyllaDB can still excel DynamoDB latencies at all of the cases. So apart from latency issues, I mentioned also performance or even capacity issues, where sometimes the capacity that was provisioned for a table might not be sufficient, and then you incur a lot of throttling of the operation. So your application is taken aback. You have to dial down operations. You have to sleep longer to retry, back off, and make sure that you retry at a later stage. And that might be a capacity, even a provision capacity issue. So there's also throttling whenever you have AWS auto-scaling. In that case, in those cases, whenever you hit those limits, that's when DynamoDB will start to scale. If you're not tweaking your table settings and telling it to scale beforehand, that's when you see those throttling coming in. You also have a lot of throttling on capacity mode, on demand capacity mode, where if you exceed the provision capacity or the expected capacity of the on-demand table, you might see throttling until DynamoDB reacts and breaks down those partitions into smaller bits. Also, there's a very common case of a hot partition. So tweaking the CloudWatch metrics, monitoring them almost 24/7 to capture those corner cases and have your team interact with the database, with the application to break down those hot partitions, or to even address them somewhat in the application perspective. There's also the very common use case of traffic exceeding the account throughput quota, where your whole account may have some quotas applied to it. Your application grows, you extend your quota, but sometimes that's still not sufficient to accommodate whole of your applications that are under that account. So those are the reasons that we usually hear more about customers that are experiencing pain with Dynamo. As I also mentioned, there's the locking issue, where DynamoDB integrates very seamlessly, nicely with the AWS ecosystem, but at the same time, that integration makes it very hard to leave the system. So what happens here is that customers are looking towards, okay, my application is running on AWS, I need a new tenant on a different provider, or I need to move my whole application to a new provider. And then even though the application can move, the database can't. So you can only run DynamoDB on AWS. And that's why our implementation makes it very easy to run efficiently anywhere. So you can run on-prem, your own hardware, your own machines, any cloud provider, not only AWS and Google, but any cloud provider that you might get your hands on. And also on Kubernetes, which makes it very easy to manage a ScyllaDB cluster if you're managing on your own. So going over the use case analysis, as I mentioned, this is a use case that is based on a streaming recommendation. So this is a machine learning generated recommendations and user targeted profiles, and those are served across the globe, and always from the nearest replicated location. So this is a streaming company. They generate those they use machine learning to generate those user-oriented recommendations, and those recommendations are stored in a database and need to be very efficiently fetched whenever the user opens up their application to have streaming titles recommended to them. In this case, we had 6 total locations, so that there are 6 global regions that had a copy of the data set, and user feedback and watch titles are also written from any replicated location. So as a user completes watching a title or likes or dislikes a title that was recommended to them, it also loops back into the database by writing that into their profile. So this is not only a read-only 6 replica use case, but there's also feedback coming from the user and changing the next recommendation cycle that is going to be generated to them. The recommendations are generated daily, so they should be immediately made available globally. So there's no time to enqueue that or do another cycle to rewrite them locally into those regions. Going over the metrics of the use case, it's a 1 petabyte data set, so that's a 1 petabyte table replicated across 6 regions as well. The average item size or payload is 10 kilobyte, so it accounts for all the titles that are being recommended, as well as various interactions that the user had with those recommendations, liking, disliking them, any sort of additional feedback or watched state that is stored alongside the actual recommendation. So as a baseline for reads, it has a 1 k-ops per second, so 1000 ops rate baseline at the lowest, and 500k ops as a peak for roughly 10 hours a day. So you see a sine wave of users interacting with the service during the peak hours and then dying down through the next couple of hours until they pick it up again. Also for writes as a baseline, accounting inclusively for those additional writes that come from the user in watch state, 400k ops per second. So that comes in from each of the sites or each of the regions, and 1.2 million writes per second for 12 hours a day, which is the batch load of the table. So as recommendations are being generated by the machine learning pipeline, it also writes that directly into the database, which then replicates across all the existing regions. A large part of the data set is overwritten, so recommendations are not being versioned on the client, on the database side. It is always being overwritten, apart from the actual user-generated content, and it's always written to a single region, replicated to other 5. So user incoming writes are always going to the local region that the reads are being served from as well, and all data is being replicated across the world, so they're very efficiently fetched when a user moves around physical and geographical regions. So as we discussed, these are the sine waves that we see from operations. In this case, you can see a little lower throughput for the data that was captured, but you can also see some spikes in the read pattern, which is when any external event happens that triggers users to be more interested in the application, open it up, let's see what I can have to watch, and then decide something to watch, and then falls into the insertion scenario. And on the left side, we have the insertion back rate, which is the batch generated data that is being written daily into the database for roughly 10 hours. So we talked about the metrics and what are the challenges that this use case faced. So the single table design, that is an approach by Dynamo recommendations, makes it complicated because you can't optimize how you write to the table, and then you have to have a single global table that replicates data across all additional tables, not only from the recommendations, which should be fairly static, generated once a day, but also from the feedback generated from the user, which are interactions locally to the region, but then replicated across all existing regions of the table. There's also unpredictable patterns, which, as I showed, there are some spikes in activity, which leads to throttling being enabled and user experience being degraded as DynamoDB adjusts or auto-adjusts to that spike in operations. The tail latency, of course, is something that you see across many use cases in Dynamo, not only for the peak time, which is obvious that it's going to be triggered, but also for any sort of P99 analysis that is done. Users are usually seeing 2 or even 3-digit millisecond latency for reads and writes at the P99. Cost as well, as you might have imagined, a use case of this size, this magnitude, using global tables will be immensely expensive, and we're going to look further into that in a bit. And also locking, because the user wanted to migrate out of the AWS ecosystem, possibly into their own on-prem data centers, and they were not able to because the database was held into AWS, and they would not need to communicate directly over the network with the database. So let's look at the cost analysis for the use case itself. We discussed the metrics, and now let's discuss the cost drivers. So the unpredictable spikes usually points to, okay, let's just use on demand because it's easier. It has a much higher throughput based on the deployment that we're looking at, 1 petabyte of data. And then that on-demand capacity is easier to get started, but can be very costly, especially when you're running at scale in this magnitude. It also has a global table with 6 total regions, 1 writing region plus other 5 replicas, which needs to be accounted for. Every write that is done to the base table has an additional cost for every region that is connected or replicated to, plus the network to replicate that data over the network to all those regions. So you pay multiple times for every write operation that is being incurred on the database. The fact that they're loading data daily is also an additional massive cost, because this additional cost means that for every item that they change, the recommendation, they need to rewrite the whole item, and that generates another data load that would generate massive cost. So replicating data across the 5 regions, as I discussed on the previous slide, also spiky reads and predictable, so that makes sense to run the use case on demand, and 10 kilobyte payloads, another driver where you cross many times the 4 kilobyte payload, so you end up with a lot of units consumed. And in this case, the estimated on demand is over $500 million a year. So this is just an estimation from the February 2025. And then looking to provision numbers, because running that workload would be fairly unattainable to run on demand mode, even accounting for replicated writes, for spiky reads, even that can be challenging on provision mode. If you assume auto scaling on provision mode, it will be adapting to those, but still, whenever the peak happens, if there's a lot of activity at a single point in time, then there's some time that AWS needs to adjust DynamoDB, and then that may end up serving or hurting user oriented workloads. So latency from users might climb, and then you would see a lot of latency, P99 specifically, from the user perspective. And this, of course, assumes reserved capacity, because that's the cheapest mode to run provision, but still it's challenging to compute all of that beforehand to reserve the capacity. And in this case, this is a little over $250 million a year, which is 2 times cheaper than on demand, but still that's the revenue of multiple small companies. So a streaming service cannot afford to invest all this money into a single database. So we discussed about Scylla, we discussed about DynamoDB and why users move, and what is the solution. So DynamoDB runs solely on AWS, and ScyllaDB through Alternator allows you to run that DynamoDB-compatible application anywhere by providing a DynamoDB-compatible API. It supports the SDKs, the data modeling, and queries, same as Dynamo, and Nadav will go further into detail in a bit, and allows you to deploy anywhere. So deploy on-premise or any public cloud, including AWS, to reduce cost. And it will get you predictable and sustained low data latencies, and all throughout removing those high operational costs that we just discussed. So with me, I have Nadav, which will go deeper into detail into how Alternator is implemented and get you a deeper dive into that technology. Nadav?
Okay, thank you. So I'll tell you a bit more about Alternator, what it is. So we started ScyllaDB in 2015, and it supported Cassandra's API, CQL, and Thrift. And in 2019, we added a DynamoDB-compatible API to Scylla. and we call that Alternator. Why did we decide to do it? So we saw that the DynamoDB API is growing in popularity. You can see on the right a graph from dbengines.com, and you can see the popularity of DynamoDB is growing and closing in on Cassandra. Scylla solves a real lock-in problem for users of DynamoDB because it runs on any cloud or on-premises and so on. And with ScyllaDB, you can now run DynamoDB apps and develop them anywhere at a cheaper cost. And also the DynamoDB API is quite close to the features of CQL that we already supported, so it was a feasible thing to do to support both APIs. So the Alternator is not a separate product from ScyllaDB. It's the same product. Just ScyllaDB now also listens for DynamoDB API requests. So those are HTTP or HTTPS requests with JSON payloads, and Scylla listens to them in addition to the CQL requests. And it's the same installation, the same setup. You just have to set some options to enable Alternator. There's an option on which port to listen, and also an option about how read, modify, write operations are isolated. But that's it. You have your cluster can support both CQL and the DynamoDB API. And Alternator is available in ScyllaDB Cloud since already June 2020. And the goal of Alternator is to have full compatibility with DynamoDB API. The goal is to just support unmodified applications that were designed for DynamoDB. So the user can take an existing application written in whatever language and using an existing Amazon SDK to make the request and just run it against Alternator instead of against AWS. And now you can run those applications anywhere. You can run it without needing to connect to AWS. You can run it on premises on different clouds and avoid the vendor lock-in. And the goal is to have full compatibility. We already achieved mostly everything is compatible, but there are some unimplemented features which we listed in this document you can find on the website. And this is just like an excerpt from it. For example, you can see that Alternator does support single item transactions, but the newer multi-item transactions feature, for example, is not supported. And you can see a list of a few things which are not supported, but the list may appear to be a bit long, but it's very short compared to the long list of things we do support. Most of the DynamoDB features we do support. Okay, so a bit more about how Alternator compares to DynamoDB. So while DynamoDB is like a multi-tenant software as a service, Alternator is like ScyllaDB. It's a dedicated installation. So you have your own cluster that is dedicated to one customer, and in the CQL world, users are aware that this is a cluster and what their nodes are, and the CQL driver can pick the right node to send the request to. But in DynamoDB, this is not the case. DynamoDB users are usually not aware that, for example, Amazon's DynamoDB, maybe it has thousands of nodes, but the users are not aware of it. And we'll discuss what to do about that in the next slide. This is load balancing, how to balance the load of the request to different nodes. And Alternator also has a powerful monitoring framework, the same as we have in like the regular ScyllaDB, that is based on Prometheus and Grafana, that helps you understand your workload's performance and get insights on how to improve this performance. Okay, so let's go back to the issue of load balancing. So usually when you have a DynamoDB application, you configure it to have one endpoint URL. For example, if you're on US East 1 region, you have this URL and you configure the application to use this URL. And you don't know which nodes exist in this region or something like that. So the application is not aware of individual nodes and can send a request to the best node because it has this data, and it can't balance the load between all the live nodes in the cluster. So we have to do something about that. So the user must deploy, the Alternator user needs to deploy some sort of load balancer, and on this slide I'll talk about the server-side solution, but the next slide will be on even better client-side solution. So server-side load balancer is, for example, you have a load balancer of TCP or HTTP requests, because I said DynamoDB requests are actually HTTP requests. So if you have an HTTP load balancer, for example, the client sends a request to this load balancer, and it forwards it to one of the live nodes at random. And from there, Scylla forwards the request to the right node, to the node that actually holds the requested data. And this works, it works nicely, but it's a rather expensive solution, because you have to you have to add the load balancer node, and each request needs to have additional hops. So it also costs a bit in latency. So it's a valid solution, but probably not the best. Another server-side solution is to have, instead of like a generic load balancer, have Scylla itself serve as a load balancer. This is a Scylla coordinator only node, a node that only coordinates the request and sends them to the right place. So yeah, so the client can go to this coordinator node, and the request is forwarded to the right node. So these are server-side load balancing solution, but we actually recommend, if possible, to use a client-side load balancer. And there, the idea is that I'll explain the idea. So usually the application uses an existing Amazon SDK. It's like a library to make DynamoDB requests in one of many different languages, programming languages supported by these SDKs. So the client-side load balancer is like a small wrapper around this SDK that basically changes the setup. Instead of while usually you set up this SDK by giving it one URL of one endpoint, for example, the US East one that I showed above, in our wrapper, you give it like one node from the Scylla cluster, and this wrapper will learn the cluster and learn the different individual nodes. But from then on, after you set it up, the application just uses unmodified API calls. So if it wants to do a get item request, it just calls a normal get item function. Most of the application doesn't need to change, just the initialization of the connection. But afterwards, the application is unmodified. And then this wrapper sends each request to the best ScyllaDB node that it can. So this wrapper maintains a list of live nodes. So if one of the nodes goes down, we stop sending it requests. It can pick a node from for example, if you have multiple geographic regions or availability zones and so on, it can pick the right node from the right region and zone. And it can pick the node that actually holds the item being requested to avoid another hop if you get to the wrong node. So using a client-side load balancer, it can lower the infrastructure cost because you don't have additional nodes for the load balancing. It can lower the networking cost if you send the request to the right, for example, availability zone instead of crossing availability zones. And it improves the request latency. So this is why we usually recommend, if possible, to use a client-side load balancer. Okay, so a little more about how Alternator works. So most of what you already know about ScyllaDB internals and how to operate it is still relevant in Alternator. It's the same product. So the scalability is the same. You can have any number of nodes in the cluster. Each node can be any size, any number of cores, and so on. The cluster can be across multiple geographic regions and availability zones. And we have a new feature called tablets that I'm sure a lot of other presentations will talk about that make it even faster and more efficient to grow and downsize the cluster as needed. So if your workload changes during the day, you can add more nodes, you can remove nodes, and it takes a lot less time to do it. You don't have to plan it like days in advance, but you can do it very fast. So Alternator is scalable just like Scylla is. All the other things you know about Scylla are still relevant. We have schemas of tables. I'll talk about this in the next slide as well. The data is stored in SS tables on disk. We have compactions, repairs, caches. We support data centers. Everything you know about ScyllaDB is also true for Alternator. So about those tables, we actually store the DynamoDB table in the same way that we store the SQL tables. So if you're curious how we do it, we have like special conventions how this actually happens in the database. So each Alternator table has its own key space. This is like a SQL concept. So if you store a table called XYZ, it's stored in a key space called Alternator XYZ and then the table is XYZ. Secondary indexes, GSIs and LSIs in DynamoDB lingo are implemented as material as views in ScyllaDB. So it's basically the same feature. And one interesting difference is that SQL needs a full schema. For each table, you need to declare exactly which columns you have and which type it has, each of those columns has. But in DynamoDB, that's not true. In DynamoDB, you just have to declare the names and the types of the key attributes. You have up to 2 key attributes, the partition key and the sort key, and you have to declare their names and their types, but the other ones you don't have to declare. So what we actually do is the key attributes we store as real columns in the schema, and they have the known types. But all the other attributes that you have in a DynamoDB item, and you can have different attributes in each item, that's also fine. They are all stored in one map, a map from text, the name of the attribute, to bytes, which is the value of the attributes. And the value of the attribute can have many different types in DynamoDB. It can be wrote here a list, a number, byte, string, and it can also be a complicated map and a map of other maps and all sorts of like nested document structures. So all these values are represented as a value in JSON. And for some types like string or numbers, we actually have like a more efficient way to store them without JSON, but the more like general types we store as JSON in in the table. Okay, so if you're curious and want to check if your application really works on Alternator, like we are saying it should, because we support unmodified applications. So you can easily try Alternator. You can create a cluster on Scylla Cloud. It's very easy, and you can also run it on your own laptop in Docker. You can see here the commands. It's like in less than 5 minutes, you'll have Alternator running. You just pull the latest version of the image and then run it and tell it to open port 8000, for example, in this example. And you have Alternator running on your laptop, and you can run your application and try it.
Okay, thank you, Nadav. So let's discuss a bit about how to migrate out of Dynamo and into Scylla. So first, let's talk about what ScyllaDB brings to the table. It's not only the DynamoDB-compatible API, which Nadav just mentioned, which is not a translation layer, so it's really performant and part of the product, and you can leverage all the goodies and performance improvements that the base ScyllaDB product receives. It's based on popular standards such as HTTP and JSON, and it is all a re-implementation of the DynamoDB API. ScyllaDB also implements CQL, which is the Cassandra query language, where the names come from, and it's all at once a query language, a protocol, and a data model. So everything from the design of the table to the queries to the binary protocol from client to server is part of the CQL ecosystem. And this is all that ScyllaDB implements. Comparing the schema and from CQL to Dynamo, CQL does enforce a schema, which is composed of partition keys, which could be more than one, a composite key, and one or none to one to many clustering keys. It also based on CQL types, native types, UDTs or user-defined types, materialized views, secondary indexes, global secondary indexes, and CDC. So change data capture is also part of the base ScyllaDB implementation. Dynamo enforces keys rather than a schema. So it has a primary key and sorting key, as Nadav introduced, and it's based on DynamoDB types, which are native to Dynamo. It also has local secondary indexes, global secondary indexes, and CDC through DynamoDB streams, which Alternator implements as Alternator streams. Let's discuss about the migration path that you might undertake. So coming from Dynamo, let's say you choose to migrate to Alternator, which is a DynamoDB-compatible API. So you will not need to rewrite your application because it should be just to point the application to your DynamoDB table to an Alternator cluster, and the table should work as is. So the design of the table and the application should just work. And then it allows you to run DynamoDB-compatible workloads anywhere. Just keep in mind that you need to look into your application to make it work with the load balancing libraries that Nadav introduced. And let's say you decided to move instead to Alternator from DynamoDB to CQL, which is a Cassandra query language. The application in tables would need to be redesigned and changed, but you would eventually benefit from a feature-rich and cluster-aware driver, as Nadav introduced, which is really aimed at high performance. So everything that the client driver does on CQL is to enable the most efficient computing possible and the most efficient communication from client to server with Scylla. So let's dive deeper into a DynamoDB to Alternator migration. So in this case, you will not need to change your drivers. Everything should be the DynamoDB compatible API, libraries, tooling, and etc. You would enable dual writes, meaning that your application should configure two instances of the connection, one of them going to AWS Dynamo and another one to Alternator cluster. You would write concurrently to both of them, make sure that both complete, retry, and the same library could be used for both of them. Alternatively, you can use DynamoDB streams to migrate writes live from the DynamoDB table. So you would enable streams, just write to your table, and replay them using Lambda or an external function to the Alternator cluster, thus duplicating your writes after they have been done by the application. After you cover the dual write portion, that's time to consider how you would migrate the historical data, or as we call lift and shift. You could read from the DynamoDB table efficiently using preferably Spark or any kind of technology that allows you to efficiently scan the whole table. But keep in mind that they consume RCUs, so your units are being impacted, and that could be costly and trip throttling. So this is really not recommended. But you could export the data to S3 and then read and export the backup and write them to Alternator. That could work. Now, let's say you chose to migrate from Dynamo to CQL. You would continue to use the DynamoDB-compatible APIs to communicate with Dynamo, but native CQL libraries, especially the ones provided by Scylla, which are shard-aware, to communicate with Scylla using the CQL protocol. Then you would do dual writes, always using each recommended library to communicate with each technology. Then it allows you to change your application, code your application to direct those writes to to Dynamo and to CQL in parallel. Then you have to figure out how to do the historical lift and shift. In this case, you could either read from the table or from the S3 export as well. But keep in mind that the native types from Dynamo and CQL are a bit different, so you would need to do some sort of ETL as you migrate your data. With regard to tuning, any library that is designed to work with DynamoDB should work with Alternator. So consider Python's Boto 3, which is extremely popular, Java's AWS SDKs or Golang, as well as Kafka connector, Spark connector, NoSQL Workbench, including our own Scylla migrator, which is a Spark-based migrator that allows you to efficiently copy an Alternator, a DynamoDB table to Alternator, or CQL to CQL. It just doesn't do the ETL portion of it. With regards to tuning on CQL, as I said, you should always aim to use the built-in shard awareness drivers, which are provided by ScyllaDB and exclusive for Scylla clusters. They're usually enabled by default, so depending on the technology that you're working with, they should just point and use or follow some small guidance on the driver implementation to enable shard awareness on your local data center. It is supported by many languages, including Rust, C, C++, Python, Go, Java, and some others as well. It is leveraged by connectors, so those connectors that are provided by Scylla for Spark and Kafka, they do offer shard awareness built in on them, so you can just use them to efficiently communicate with a ScyllaDB cluster. And it's important as well to mention that the Scylla CQL drivers are rack aware. So that means that your client can be smart enough to communicate with the nodes that are local to the AZ that the application and the cluster are deployed in, so you avoid cross AZ traffic as you communicate with your Scylla cluster. I mentioned a bit about the migration challenges that you might face as migrating, but we're just reiterating the importance of avoiding throttling your application, your tables, and impacting your application and increasing costs. So this is something that most customers do. They just point the migrator to their table and start reading data, but at some point, those units are exhausted, latency climbs, autoscale kicks in, and then the application grinds to a halt because everything is being impacted. So keep that in mind. But also from reading from S3, which is the other option that we discussed, keep in mind that if you're using a single export from S3, which is native from AWS, that should work. But if you're doing it any other way, if you're exporting using an external library or any sort of additional backup or any queuing that you might have, be aware of the JSON standards and how that interact with the data types that are native to Alternator, to DynamoDB, and to CQL. So there might also need to be some additional ETL that goes on as you read those JSON files. And also keep in mind that as Dynamo, especially if you're migrating to CQL, as Dynamo is a schema-less design and Scylla does enforce a schema, especially on CQL, keep in mind that the schema changes over years. So if your application has been running for a while, there might have multiple iterations that changed how data was stored, and that could impact your migration process as well. So we discussed about why users move out. We discussed about DynamoDB cost. We reviewed Alternator and how it's implemented. We discussed migration. And now let's look into what the ScyllaDB cost would be for the use case that we discussed initially. So you would expect me to say 42, but no, the answer is 50%, and that's guaranteed. So it's a project that will analyze your workload with you. And if it's lower than 50, then you pay whatever we size you for. But if it's higher than 50%, we'll discount you at 50%. So take a look at the link on the screen if you're interested, and talk to our specialists in order to size and price your workload for you. This is generic campaign for pricing, but going deeper into the estimation that we discussed earlier, this user moved from AWS into on-prem hosting. So all the hardware, networking, and inter-site networking was owned by them. So they could cost, the cost was really shared across all the applications, databases, and users on their network. And then they migrated the application and Alternator, and DynamoDB into Alternator on-prem, keeping total 6 regions and replicating data across all of them. The yearly cost for this solution on-prem, including infrastructure, meaning the hardware that the servers are running on, $24 million, including Scylla licensing plus the hardware itself, but not including management or networking or additional variable fees that are harder to estimate and to share. That number is 24 times lower than DynamoDB on demand, which is the crazy way of deploying that application, but still 11 times lower than DynamoDB provision mode, which is the cheapest and most sane way of deploying the application on Dynamo. But still, we can see that it's still 11 times costlier than deploying that on ScyllaDB. And if you look at the graph on the right, you will need a magnifying glass to see the bar for ScyllaDB just at around the 24 million. So it allowed the customer to be very cost efficient in their dedicated infrastructure, dedicated hardware, and still improve their latencies and increase performance. To wrap it all up, Scylla can help you if you're experiencing on Dynamo high cost, unpredictable latencies, and locking if you need to move to any cloud or on-prem. And DynamoDB can have its upsides. It's really easy to get started, but it usually ends up hurting users that are running that at scale. And Alternator is in here to reduce friction to moving out of Dynamo. You can just take your application, point it to an Alternator cluster, and enjoy the performance, the cost reduction, and the improvement of latencies as you move your application. And while Alternator removes the friction, CQL is very featureful, so it's also worthy for you to look into that so you can leverage those in your applications. So thank you very much, and stay in touch. Nadav and my contacts are on the screen, and talk to you soon.